Hi and welcome to video 6 on this Unit 4 Topic 2 Differential Equations Specialist Mathematics video series. And in this video we are talking about applications of differential equations, and I'm going to talk specifically to you about Newton's law of cooling, which is a really important application and does come up a bit, could potentially come up certainly in your external exam. So Newton's law of cooling is a law about how things might cool or heat up in the natural environment. So if you have something that is hotter than the surrounding area or cooler than the surrounding area, how does that eventually become the same temperature as the surrounding area? Now I've got a bit of a diagram there and hopefully you can see it. The important thing here is that Newton's law of cooling specifies that the rate of change of the temperature of whatever this thing is, this purple line, is proportional to the difference between the temperature at that time and some base temperature, which is probably room temperature, so wherever it's heading. So you can see it on here. What I'm saying is that at the start it cools quicker. The rate of change is quicker because the difference is bigger. And as we get further on, the difference decreases and therefore the rate of the change decreases. So you can see the tangent here is steeper than the tangent there. And that makes sense. Take some time to think about it. Of course, you would expect something to cool down slower as it gets closer to room temperature. Now, mathematically and theoretically, it asymptotes with room temperature. It never actually reaches room temperature, which is a bit silly, but remember, room temperature is not constant. So it doesn't really make sense for that to happen. In the real world, if you've got a cup of coffee at home, it will cool down, but the room temperature might increase a bit at some point, and eventually it will be room temperature, and that's dumb. Okay. There are other factors that change the rate of change, such as the insulation matter, if it's a cup of coffee, depending on the type of cup it's in, those types of things. But that's fine. We don't have to worry too much about that because we actually are looking at situations where we know enough about the data to disregard the contextual side of things. We don't have to have constants of cooling based on insulation materials or anything like that. We just need to worry about the fact that we know some data, we can build a differential equation. So let's have a look at a scaffolded example, and I've written a little note here to say that this is scaffolded, so therefore it's a complex familiar at best. Okay, so part A is asking you to construct a differential equation. So in terms of constructing a differential equation, we need to bring in Newton's law of cooling here. And that is that given this information, an iron bar placed in a room, so there's room temperature, iron bar has that temperature initially, and we know this piece of data. So I might just make a note of those. T0 equals 80 degrees. And T5 equals 70 degrees. And of course, I should also define my variables here. And that is that little t is equal to the time in minutes, and capital T is equal to the temperature of the iron bar in degrees Celsius. So that's important as well. I also know that room temperature is equal to 20 degrees, and this will be my asymptote. So I have a rate of change of temperature with respect to time is proportional to temperature minus room temperature, which is 20. It's proportional to the difference between the temperature at that moment and whatever that stagnant temperature is, which is usually room temperature. And so we get this. dt d little t is equal to k t minus 20. Some constant times t minus 20. That's the definition of our proportional term. And that's actually the answer to part A. Now in part B, we're asked to solve the differential equation. And we have some known values. So we're going to be solving and finding k, and also we'll have an additional unknown. So we're going to go through and do that now. So first of all, I'm going to write down that dt over t minus 20 is equal to k d little t, and then I'm going to integrate both sides. So this is me splitting this differential equation up to get the capital T values on one side and the little t values on the other side. And of course this is equal to the natural log of t minus 20 divided by the derivative of the inside, which is just 1, equals kt plus some constant c. And you've seen in previous videos that I can now write this down as t minus 20 equals e to the kt plus c, and that's equal to a e to the kt. And now I can write down t is equal to a e to the kt plus 20. Now this, you'll do a few of these questions and this will look quite familiar. Now the 20 will change, and the k might change, and the variables might change, but look quite familiar. You really can't, in an external exam, unless you're told otherwise, you can't just jump straight to this formula. So just be aware of that and make sure that you don't just go jumping straight to formulas. You've got to build it from differential equations because that is the content area you're dealing with. So we know that T naught, and I've actually written these wrong, so that should be capital T really, shouldn't it? So the temperature at time 0 is 80 degrees. So we know that T naught is equal to 80. And so therefore at time equals 0, we get 80 equals a e to the k times 0 plus 20. So if we have the initial value, it really helps. And we're getting a special value for a now as well. 60 equals a e to the 0. And therefore a is equal to 60. So a doesn't equal the initial temperature this time like it has done in previous examples. Instead, a equals the initial difference, and that will be an important feature as well of your work. Okay, so we get therefore capital T equals 60 e to the kt plus 20. And we also know that T5 is equal to 70. So I can now find my value for k. So I get 70 is equal to 60 e to the kt plus 20, which means that 50 equals 60 e to the k times 5. I should have put 5 in. Which means that 5/6 is equal to e to the 5k. And that means that 5k is equal to the natural log of 5/6. And k is equal to 1 over 5 natural log of 5/6. And I also have a value for that. That's approximately equal to negative 0.036, which I can use, or I could use my exact value. And I might just maintain the exact value throughout here. So I'll just make a little bit more space. We're pretty close to done, but a little bit more space. So that's part B to build that function. And so I'll write it out. The temperature is equal to 60 e to the log 5/6 t over 5 plus 20. And I could write negative 0.036. And it's good that it's negative because, of course, this is a decaying model. It's going from 80 down towards an asymptote. So there's my model, and there's part B. Part C, sketch a graph of t against t. Now, I won't go into a lot of detail here, but I'll just pop part C over here. The graph is going to look pretty standard. I'll make sure I've got all 4 quadrants, but I don't need them in this case. And this is my temperature. This is my time. And I know something about 5, so I'll put that there. 10. I know that my asymptote is here at 20. Let's see if my scale is 2, 4, 6. And I know that I start at 80. And then I know that 5 minutes it goes down to 70. So I might actually make that 10 and this 5. So it's always good to do a bit of planning. 5. 70 is there. And it's going to run along and smooth out there. So there's a bit of an understanding of what my model looks like and what's going to happen. As we expect, they always look pretty similar. And part D. How long does it take for the bar to cool to 40 degrees Celsius? So we know, we want to know when does T equal 40? That's a pretty easy question. We just put 40 into here. 60 e to the log 5/6 t over 5. You can even leave k in here, to be honest, because it's a bit of a muck around having that exact value. So I get 20 equals 60 e to the log 5/6 t on 5. And then I get a double rearrangement. I get log 5/6 t, that's not inside the log, on 5 is equal to the natural log of 2 over 6. And that gives me t. I do that rearrangement again, and I get a t value of 30.52 minutes. Which makes sense because it dropped from 80 to 70 in 5 minutes, so it's going to take a bit longer to go down to 40. And of course, the rate of change is slowing down. And let's see how that matches my graph. 40 here. Oh, poor graph drawing. But anyway, that's all right. So that's the end of that example. I'm going to stop this video here and we'll move on and do a couple more examples in video 7. All the best.